Hi people, this is a short video segment that I'm doing to show you how to uh, perform an elastic plastic analysis for a very simple geometry, which is just a bar, where you have the data specified uh, as in terms of the strain rate values. Okay, so you have tables of stress versus strain, and those are for specific strain rate, and then you have several of them, and you want to perform a, for example, static or a dynamic analysis. In this case, I'm going to do static analysis. Now, uh, this kind of thing is because the solver, FEA solver in 3D Experience is actually the Abacus program, the stripped down version of the Abacus program. These are fairly well established in some of the training documents and tutorials that you see on YouTube for Abacus. Now, for 3D Experience, basically, you have to do some detective work and see how things are done in CAE, Abacus CAE, and translate that into the new interface and new icons of 3D Experience. Okay. Now, later on, I will do this problem, but not in terms of several sets of data for each strain rate. We'll do it in terms of a Johnson and Cook model. Okay, but here's the problem. The specific problem that I'm going to do is a bar with the dimensions that's given to you, and you'll see that there will be three planes of symmetry here. Just bear with me for a second. So the three planes of symmetry are shown here, and one end of the bar is subjected to a displacement of two millimeter, which is taking place in 5 seconds. In 5 seconds, okay. Now, if you look at this, the strain rate here is the strain divided by the time times covering the period, and that is strain is 2 millimeter over 50 millimeter, and the rate to get the rate you divide it by the duration of the time, 0.008 per second. Now I'll come to that in a second. By the way, this problem that you see up there is really a bar which is twice as long, okay, and twice as, let me see, dimension-wise, twice as thick, as you can see, which is pulled on both sides. But because of symmetry considerations, all we need to do is 1/8 of the model. Then you have three planes of symmetry that I showed in the previous slide, and just the displacement appears only at this end, okay? The data that I'm taking is fictitious data taken from this site. Very good presentation there, uh, down below here, okay? And elastic modulus are standard for steel. And this is the 5 sets of data that I was talking about. See that? There is the yellow one, which is for strain rate of 0.001. The orange one, strain rate of 0.1. Blue, strain rate of 1. And then the next one, the green is 10, and then 100. Okay, these are plotted here. You can see that. By the way, you need static yield strength, which I'm going to assume is 24. I mean, you can use this if you want, but I'm going to assume it's 24. Okay, so we're going to do this problem. All right. So let me start with a part file. Okay, let's go ahead and make the part. So on that vertical plane, I will sketch a square which is 5 millimeter by 5 millimeter. So let's dimension this thing. So that is 5 mm, and this is also 5 mm. Okay, exit and pad it. Pad essentials, pad that sketch. Okay, by 50 millimeters. Okay, that is our part. Now, a couple of comments that I have to make. One is I just realized that in this slide that I showed you earlier in on the tutorial, there was a typo here. This true stress should have been 26.6, and I changed the static yield strength to 26 megapascal also. So this was a typo. I corrected that. The other thing is that because the true stress is in megapascal, I'm going to change my units of stress because when you import the Excel file, and that's what I'm planning to do, that column is going to be megapascal. So I'm going to go to preferences. Excuse me. Okay. It'll pop up. The window will pop up. Okay, right there. And I'm going to type stress here to find it, filter stress. Right there, stress. From Pascal, I'm going to change it to megapascals. Otherwise, in the Excel spreadsheet, you have to specify that that column is in megapascal, and I decided not to do that. So I'm going to change my units right here. Okay, let's go ahead and create our material. So tools, uh, create material, and I'm going to call this thing massaged Excel, and I'll tell you what I mean by massaged Excel. Okay, so okay. Now, all right, so where is this thing? Massage should be massaged Excel. Okay, apply, not messages, massage. I'm going to close that, apply it to this part, green check mark to accept it. Okay. All right. The reason I called it massaged Excel. Let's input the values first of all. We go to structures under abacus multiphysics, under mechanical, elasticity, elastic. First of all, the Young's modulus is, notice that the unit is 200. The unit is megapascal, so that's going to be 200,000 megapascal. Poisson ratio 0.37. Let's say these are fictitious materials, so don't let it bother you. Now, when you go to plasticity, metal plasticity, plastic, okay, so what happens is that we have information that is strain rate dependent, so I'm going to check this box. Notice that an additional column has been created here, okay? And instead of typing things in, I'm going to import an Excel file. Now, this Excel file must have a particular format, so it can't be something like this. So let me show you what I want. What kind of thing do I want? So let's go here. All right. So it's going to be three columns. First of all, the first column must be true stress. Second column true strain, and third column strain rate. Okay. So it's the same information that I showed you here, except that they have been massaged so that the yellows are there. This is a strain rate of 0.001, and then 0.1, and then strain rate of 1, etc. And I didn't specify my units here. That's why I actually went and changed my units in the preferences. Now, the other thing is that I added a first row here. That first row is just a header. It's not going to be even read into Excel. Okay, let's start with the second one. Now, I added a row which is the yield strength at strain rate 0. Okay, that is what is called static yield strength. You need this. You need a initial row before all the data that you have provided. Okay, so yield strength at strain rates at strain of 0, and strain rate static means that it's pretty much very slow. Again, it doesn't have to be 0. It can be very small number. Uh, but here, that is this information. Static yield strength 26 megapascal. Okay, good. So let me close this. You go back there. You say right click, import, and it's this massaged Excel file. Now it tells you that I didn't specify the unit in column 1, and therefore MPa is going to be used, which is the default in the preferences. I changed it, remember? And same thing about the last one, strain rate unit of per second. It was not specified in the Excel spreadsheet, so it's going to use the default, which is per second. That's exactly what I want. So that takes care of everything. Okay. So basically, there's going to be 3 Excel files. It could have been, one after another. 1 Excel file, 3 sets, 3 tables. So we say, okay, very good. This is done. So now we're going to go and mesh this thing. Structural model creation. It's a solid mesh, so I'm going to use this standard. I'm going to be using quadratic or parabolic. The size that I'm going to specify is 5 millimeter. Remember here I said each element is 5 by 5 by 5, okay, millimeters. And the number of layers, well, we'll see how it goes. We'll have to change this thing to a different number if it doesn't look like what we want. So we say, the selected geometry. Don't forget to select the geometry. Okay, there is the part selected, and we say update. Okay, notice that they did put 2 layers through this thing. I did not want that, so I'm going to go back here, change the number of layers to 1, and okay. And if you want to update it, it's going to be exactly the mesh that I had in mind. Very good. That takes care of the mesh. So now we're going to go to the structural scenario creation. We're going to select our finite element model, the mesh that I've created. Great, good. We go to procedures. So we are doing static analysis, right? We're doing static analysis. Static analysis. Now the time here is a dummy time. It really doesn't matter. This is static, okay? It's a dummy time. And what we want is, first of all, I'm going to uncheck the include geometric nonlinearities. Actually, no, let's not do that. Let's leave it in. For the initial time, I'm going to use 0.01, and it can increase it, of course, up to a maximum of 1. We're just not going to do that up to a maximum of 1, but it cannot go below that. So I think we have all the information that we wanted. Yep. How about the restraints? We have 3 planes of symmetry. This is for the plane of symmetry right there. So let me do the following. First of all, let me hide the elements. Let me hide this, just the part. So now we're going to go restraint, planes of symmetry, 3 of them. This is one of them. You have to do these one by one. I don't think you can do it at the same time. Of course, it makes sense because the normals are different. Okay, and then at the end, the very end, this is also plane of symmetry. So we have 3 symmetry conditions. Okay, and we're going to pull this thing. So under the load is a translation, apply translation on that face. Now, what did we have here? We had 5 where was it? 5 millimeters. 5 millimeters. Okay. Incidentally, let me also go ahead and change the time to 5. Okay. Uh, it is true that you're not doing a dynamic analysis, but this 2 millimeters is not specified in 1 second. It's in 5 seconds. So with your permission, I'm going to do this thing. First of all, it's going to be 2 in the direction Y. in the direction, right translation, degree of freedom in direction y, okay, 2 millimeters, and that's pretty much it. The only thing is that my time, I have to go change it here. So under static step, because if there's any meaning to using the data and interpolating, at least the strain rate must be meaningful, okay? So it's 2 millimeter over over a 5 second interval. Otherwise, this does not make sense, okay? All right, so let's see now. We have the restraint, we have the load, and let's go to simulate. Let's see what exactly is it that we want. We want output. We want the stresses to be recorded in addition to default information and strain. Now, when it comes to strain, we can do the total strain or we can use the plastic strain component. So it all depends on what is it that you want to plot later on. I will use total strain. Uh, how about also plastic strain? It really this depends on what exactly is it that you want to do. Okay. A total strain means on top of that there is the elastic strain that is superposed, which okay, good. As I said, this was unnecessary unless you want to plot specific information. Plastic strain, for example, in the direction Y, in the direction X, Z, or you know, the equivalent one, the magnitude, etc. That's pretty much it. So let's go ahead and run it. Let's do a model check first. It's a fairly straightforward problem. The whole purpose of this video was to show you if you have data, experimental data, and you want to input it into a 3D experience to do elastic plastic analysis, and that experimental data is strain rate dependent, how do you go about doing it? Something happened here, simulation checks failed. For more information, so let's see what the problem could be. Okay, so it looks like I have lost my connection, so I'm going to, okay, I logged out and reconnected, so let's see if it works this time. I got FEA licenses, and I suspect that I was logged in for a long time without activity, and it probably disconnected me. Let's see how it works. Here comes the moment of truth if I get any errors in licenses again. So far, so good. Yeah, I think that's exactly what happened. Starting simulation solver, very good. And let's check the iterations, see how it's going. See, it started by 0.01 and very quickly it all reached the end, okay? It's a very simple nonlinear material without any contact, etc. So there we are, so we close this thing. Now this, of course, is the uh, von Mises stress. It's a bar, so everybody is going to be the same. Of course, the initial, and then all the other ones are all going to be different numbers, but they're all the same color because this is a bar everywhere, and because of the restraints that I have, is it's going to be a perfect uniform color. Now, if you go to displacement, on the other hand, there we are. You can say 2 millimeter displacement over a 5-second interval. Uh, this is not real seconds, real time, but and then you can also plot other stuff such as, for example, let's see, plastic strain. So uniform plastic strain, we know that, but nothing surprising about that. Let's see now. Let's check the. So everything has yielded. We already know that. Okay. So anyway, I hope that this was useful, showing you how to input strain rate dependent data into the 3D experience, and you can generate two-dimensional plots if you want, etc. Okay, good luck. I will do this problem in the next video segment, but not using the direct data, but using the Johnson-Cook model, which is based on the fitted data of this problem.